Hello friends, welcome to Learners Forum. So in last video we saw about what is a basic rectifier and certain characteristics about a rectifier. So from this video let us see the types of rectifier starting with half wave rectifier. So from the name itself we can understand, we know what is a rectifier. It converts an AC signal into its pulsating DC. Half wave in the sense only one half of the cycle will be rectified in this particular type. So when we consider the two cycles, positive half cycle and negative half cycle, in half wave rectifier only the positive half cycle will be rectified. That is, only when we have the positive half cycle the respective AC will be converted into pulsating DC, whereas in the negative half cycle the signal will be simply eliminated. So we will have rectification process under the one half of the cycle. So looking on the basic circuit diagram, we will have a source of AC voltage here. So here we will use either a step up or a step down transformer, but mostly step down will be used. So here we will get the required AC voltage. So that is applied across the particular rectifying element, which is nothing but a diode. And after this particular rectifying element, it is passed into the resistive load. That is, as we have seen before, we will be connecting a resistance in series along with the load. So we have taken a load resistance over here. So here we will have a single phase AC supply as a source of AC voltage, and here in the rectifying element this AC voltage will be supplied to the particular diode, which is having an forward resistance of RF, and third part will be the resistive load, where we will have the voltage across the particular element as EDC, and the load current flowing here will be IL. So this is the basic construction of a half wave rectifier. So we will have all the three elements, that is the source of AC voltage, rectifying element and resistive load, to be connected in a series way. So using a suitable step up or step down transformer, like I said before, mostly step down will be used. Here the AC voltage is applied to the rectifier circuit. So this half will be the rectifier circuit, and the applied AC voltage will be sinusoidal with a frequency of 50 Hz over here. So this is the basic construction of a half wave rectifier. So here the transformer that we have used will decide the peak value of secondary voltage, which is given by N2 by N1. N2 refers to number of turns in the secondary winding and N1 refers to the primary winding, which is equal to ESM divided by EPM, where this ESM and EPM refers to peak value of primary and secondary AC voltage, and N1 N2 refers to the number of turns. So this particular voltage ESM will be sinusoidal. The instantaneous value will be ES, which is equal to ESM into sine omega t. So like I said before, the value of RF is nothing but the forward resistance. So this is the basic construction of a half wave rectifier. Now let us see the circuit operation, that is the working principle of a half wave rectifier, how the positive half cycle is rectified and how the negative half cycle is eliminated. So under the circuit operation, we can divide it into two cycles. So what happens when it is in the positive half cycle, and let us see what happens in the negative half cycle. So whenever we have positive half cycle, the diode will be under forward biased condition as we have seen earlier, and the current will flow in clockwise direction. Whereas in negative half cycle, the diode will be under reverse biased condition. So the common thing is, whenever the diode is in reverse bias condition, there will not be any flow of current. That is, it will act as an open circuit. So the total load voltage will be equal to product of load current and load resistance. So when we know the values of the two things, either current and resistance, then we can calculate the voltage, or in case if you need to calculate the value of load current, knowing the values of load voltage and load resistance, you can use this relation. So looking at the circuit operation, we can identify how the positive half cycle is converted into its equivalent pulsating DC and how the negative half cycle is getting eliminated. So this is the basic circuit of a half wave rectifier. So here we are applying a positive half cycle. So here it is having only the positive half cycle, which is applied to the transformer, and through this we will have an AC voltage applied to the rectifying element, which is nothing but a diode, which is mentioned as D here. So A and B will be the terminals over here. So whenever we have positive cycle, the terminal A will be positive and the terminal B will be in negative value. and it is applied across the rectifying element diode, and then we have a load resistor which is connected in series. So under this condition, the diode will be in forward bias condition, and we will get the same kind of positive half cycle in the load resistance value. That is, we will have the equivalent DC value. But whereas when we consider it for a negative half cycle, when we apply the negative half cycle to the same kind of AC voltage, that is, we have a AC voltage supply here, and then it is moved into the rectifying element. So when we apply negative cycle to the same first half of the circuit, here the diode will move into the reverse bias condition, which means it will not conduct. So we will have an open circuit over here. Since it is open circuited here, the output value of voltage will be 0 volt, since there is open circuit connection. So this is what happens between positive half cycle and negative half cycle in an alternate manner. Looking into the waveform, we can consider a basic AC voltage signal. So here we will have the secondary voltage ES value with the maximum magnitude of ESM. So whenever the diode is in on condition and off condition, you can see the narration over here. So during the positive half cycle, the diode will be in on condition, and during the negative half cycle, diode will be in off condition. Like I said before, similar thing will be getting repeated for every half of the cycle. So again we will have a positive half cycle, so it will be under on condition, and for the second half cycle, that is in the negative half cycle, diode gets turned off. So whenever this process occurs, we are calculating the value of load current and load voltage now. Load current in the sense we are calculating here, which means whenever it is under positive half cycle, the diode will conduct, so we will get the required value of signal over here. Next, it is under negative half cycle. So whenever it is negative half cycle, the diode will be under open circuit condition, so we will get a 0 value. So it will be just a straight line. And again we have a positive half cycle for which the diode conducts, so we will get the required same amount of signal. So there will be a positive signal, and when it is in the negative half cycle, again open circuiting condition, so we will get a 0 value represented by a straight line. Next is load voltage. So when we calculate the voltage across the load, it will be similar to the condition of load current. So we can use the equation directly instead, which is nothing but load voltage, which is equal to load current into load resistance. We know the value of resistance and we know the value of load current also. So whenever we will have the value of load current, we will have the value of load voltage also. So again it is represented with the same waveform. So here we have a maximum value of Im. So here we will have the corresponding value in terms of voltage. So here it is 0. So for the second half of the cycle, again the load voltage also will be 0, because even if the value of load resistance is finite, here the load current is 0. So 0 multiplied with any finite value of load resistance will be again 0. So we will have a same waveform like the load current also. So this is the waveform for load current, and this is for load voltage. Now let us see what happens when we calculate the voltage across the rectifying element, that is diode. So I have said before, when we saw about the characteristics, that is when we are calculating the voltage across the rectifying element, we will have a voltage called as peak inverse voltage. That is, whenever it is reverse biased, we will still have a reverse voltage value having a maximum value. So that peak value which happens whenever the voltage is reverse biased is termed as peak inverse voltage. So whenever we are calculating the voltage across diode, it will be just opposite to the value of load voltage. So here reverse biased in the sense, here you will not have any conduction, which means here we will have a 0 value, whereas during the negative half cycle it will have a small peak value representing the reverse voltage. So when it happens in the negative half of the cycle, we will have a waveform in this way. Again for positive cycle it will be 0, and for negative half you will get the waveform in this way. So make sure that you understand the waveform very clearly. For load current and load voltage, it is calculated after the rectifying element, that is after the diode value that we have seen in the circuit diagram. But this is calculated across the diode itself. So that is the reason we are getting an alternative waveform when we compare to load current or load voltage. So this is the working operation of a half wave rectifier. So before starting with the complete detail about the rectifier, I said how it is differentiated based on pulsating DC and DC signal. So the DC output waveform is nothing but a straight line which happens only when it is in ideal condition. But the DC output waveform, when we consider for practical condition, will vary, which will have positive sinusoidal pulses. That is, for ideal condition we will get the waveform, that is the signal in this way, whereas in practical condition we will get for half wave rectifier as this one. This is nothing but sinusoidal pulses, that is positive sinusoidal pulses, which is nothing but it is a kind of pulses, but here it is a kind of a DC signal, so we call it as a pulsating DC, which is nothing but a discontinuous signal. AC will be a continuous signal and DC will be a discontinuous signal. So this is for ideal condition, but for practical condition we will get in terms of positive half pulses, like we have seen just before in the waveform also. So this is nothing but a pulsating DC and DC signal difference. So that is why we define a rectifier as a device which converts an AC signal into pulsating DC and not just a DC signal. So this is the ideal and practical condition difference. So make sure that you know the difference between what is a DC signal and a pulsating DC signal. Now let us analyze certain parameters about half wave rectifier. So the first one we are going to consider is about average DC load current represented as IDC. So this value can be obtained by integration. That is, we are determining the area under the curve for one complete cycle for 0 to 2 pi, and then we divide it by the base value of 2 pi. So for a single area we are analyzing and then we are just integrating, so that is why we have represented as this value has been obtained by integration. So in equation wise we can represent the load current IL is equal to Im into sin omega t, which is for 0 less than or equal to omega t less than or equal to pi. That is, if we draw the sketch we will get in this way for 0 to pi and for 2 pi. So for 0 to pi we will have a positive half cycle over here. So this value will have a magnitude of Im, and since it is a sinusoidal waveform it is represented along with sin omega t. And for the second half of the condition, for that is for pi to 2 pi, we will have a value which is nothing but 0. So it is taken as 0 for this particular range. So this is the value of load current. So now to calculate the value of average DC load current IDC, we have to integrate with respect to the base, which is nothing but 2 pi. So this is done by integration. So integration is taken over here and the range of integration is taken for the limit from 0 to 2 pi. So 0 to 2 pi, what we are going to integrate is this load current ideal. So ideal in terms of d omega t, and we are dividing it by the base value, so 1 by 2 pi. Substituting the value of IL over here, it is nothing but Im sin omega t d omega t. So we saw about the different values for the different range of load current values. So for 0 to pi we have a standard value, and for pi to 2 pi it is 0. So we can split the integration in that way. So for 0 to pi it is Im sin omega t d omega t, plus from pi to 2 pi it is 0. So we can stop with that, and it is divided by 2 pi. So integrating the first half of the signals, that is from 0 to pi, we will have Im sin omega t d omega t. So if you integrate sin, we will get it as minus cos omega t, and the range of limit will be from 0 to pi. So we can take the value of Im outside the integration. So Im by 2 pi into, after taking the negative sign out, applying it as upper limit minus lower limit, we will get cos pi minus cos 0. So cos pi value is minus 1 and cos 0 is again 1. So minus 1 will be minus 1 minus 1, which is minus 2, and we can divide that 2, and minus of minus will be plus. So the remaining value will be just Im divided by pi. So the average value of DC load current IDC is equal to Im by pi. This is the average value. So if you apply KVL to the complete circuit of half wave rectifier, then we can get the value of Im as ESM divided by RF plus RL plus RS. So RF is the forward resistance which we take it for rectifying element, that is diode. RL refers to load resistance and RS is nothing but the resistance of secondary winding. So in case when you are supposed to solve any problem based on this particular equation, you have to check for the value of RS. In case if RF is provided, you can use it directly in this formula, substitute for the different values, calculate Im and divide it by pi to get the value of average DC load current. And in case if it is not provided, you can simply neglect that and just apply the value of RF and RL along with ESM and calculate the value of required Im. So this is the average DC load current value. Second parameter, average DC load voltage EDC. So it is represented as product of average DC load current and load resistance. So DC load current we have calculated just now, which is nothing but IDL, and load resistance is RL. So multiplying the two things, we will get the required DC load voltage EDC. So IDC value, which is calculated as Im by pi into RL, and we know the value for what is Im also, which is ESM divided by RF plus RL plus RS into remaining pi into RL. So in this condition, the source resistance and the RF, that is the secondary winding resistance and forward resistance, will be very less than the load resistance value RL. So using this particular condition, we can further simplify the value of EDC as ESM divided by pi into RF plus RS divided by RL plus 1. So this ratio of RF plus RS divided by RL will be very less than the unity. So we can simply neglect that and further simplify the value as simply ESM divided by pi. So the DC load voltage is equal to maximum peak value of secondary winding ESM divided by pi. And for load current, that is average DC load current, it is IDC, which is equal to Im by pi. So this is the different values of DC load current and DC load voltage. So in case if you are supposed to solve any problems based on these two parameters, we have a small note for that, that is, do not calculate the value of EDC as ESM by pi directly whenever we have the finite value of RF and RS. So in the question, just look for the value of RF and RS. In case if you have a finite value of these two parameters, then you have to completely apply that in this particular equation and solve for the required value of EDC. So this is an important note. So we have seen RS and RF also. If it is not provided, you can simply neglect and use this particular relation. But if it is provided with a finite value, then you have to make sure that you use these equations. Next parameter is about RMS value of load current, that is IRMS. So before starting out with the actual value of IRMS, let us discuss what is RMS in basic first. RMS refers to root mean square. So if you are supposed to find the RMS value for a particular parameter, you have to take a square of the signal first, then take the mean and then take a square root. So this is the order to find out the value of RMS, which is root mean square. Now let us calculate the value of IRMS, which is nothing but square root of 1 by 2 pi integral 0 to pi Im sin omega t square d omega t. So as I said before, first we are calculating the value for current, that is the RMS for the current. So we have to take a squared value of current first. So the squared value of load current is Im sin omega t square. Then you have to take the mean value. So it is integral of 0 to pi divided by 2 pi. And third thing is you have to take square root. So we have a square root over here. Now let us calculate to find the actual value, which is square root of 1 by 2 pi integral 0 to pi Im square sin omega t square d of omega t. So here we can take the Im square, which is out of the integration range because it is a constant value. So you can take that, and we have a square root also. So after taking square root, we can simply write it as Im into square root of 1 by 2 pi integral 0 to pi. For sine square, we can write it as 1 minus cos 2 omega t divided by 2 into d omega t. So now we have to split up these two terms and integrate it separately to get the actual value of IRMS. So IRMS is equal to Im into square root of 1 by 2 pi. So integrating the first term, we will get it as omega t by 2 minus the second term, we will get it as sine 2 omega t divided by 4, and the range of integration will be from 0 to pi. Solving this further, we will get Im square root of 1 by 2 pi. Simplifying this, that is after applying upper limit minus lower limit, we will simply get it as pi divided by 2. So this will be simply equal to Im divided by 2. So here we have to know a small thing, that is the root mean square of half wave rectifier is equal to Im by 2. Whereas if you consider for full wave rectifier, the same IRMS will be equal to Im divided by root 2. So this is for full wave rectifier. So the questions will be with a twist in this condition only. So in case if you have any question where you are supposed to calculate the value of IRMS, the question will be like calculated the IRMS value. But you have to make sure that you are checking it for either it is half wave or a full wave. So for half wave it is Im by 2, and for full wave it is Im by root 2. So this is the basic difference. So when we see about the full wave rectifier, we will calculate the IRMS value again there also. But here I am just telling you to know the difference for half wave rectifier and full wave rectifier in terms of IRMS value. Next is DC power output PDC. So it is nothing but product of, usually power is nothing but a product of voltage and current. So it is E into I. In terms of DC, so it is EDC into IDC. Again you can represent E in terms of I into R. So it will be I squared R after multiplying with IDC over here. So IDC square into RL. So we have calculated the value of IDC just before. So we can apply the value of IDC, which is nothing but Im divided by pi the whole square into RL. So which is Im square divided by pi square into RL. Again the value of Im is a question mark there. So Im, which is nothing but ESM divided by the total resistance value RF plus RL plus RS. So applying that, we will get the net DC power output PDC as ESM square RL divided by pi square into RF plus RL plus the whole square. So this is the net value of DC power output. Likewise, we can calculate the AC power input also. So the AC power input is nothing but the power input from secondary of transformer, which is applied to load resistance, forward resistance and source resistance. So PAC will be equal to IRMS square into RL plus RF plus RS. So here we know the value for IRMS, which we have calculated just now. Applying that, we will get it as Im square by 4, because the value of IRMS is nothing but Im divided by 2. Applying that, we will get it as Im squared by 4 into RL plus RF plus RS. So this is the value of AC power input PAC. Next is rectifier efficiency eta, which is nothing but ratio of output DC power to input AC power. So we have calculated the output DC power separately and input AC power separately. So now let us apply the value of DC output power and AC input power and calculate its ratio to get the rectifier efficiency, which is PDC divided by PAC. So the value of PDC is into RL divided by the value of PAC is Im square divided by 4 into RF plus RL plus RS. So simplifying this, we will get it as 4 by pi square into RL divided by the total resistance, which is RF plus RL plus RS, which is further equal to, after substituting for the value of 4 by pi square, we will get it as 0.406 divided by 1 plus RF plus RS divided by RL. So this is the net equation for rectifier efficiency eta. So this value, considering RF plus RS, which is very less than the load resistance RL, the percentage of maximum efficiency will be 0.406 into 100%, which is nothing but 40.6%. So this is the rectifier efficiency value. So in a half wave rectifier, the maximum 40.6% of AC power will be converted to DC power in load. So the remaining 60% of power, in the sense it will be a question mark. So this 60% of power will be converted as ripples in output, which is nothing but the fluctuating component. So this is the maximum rectifier efficiency, which is 40.6. So we have to remember this value because sometimes questions can arise from this particular data also. So the half wave rectifier will have an efficiency of 40.6%. Let us see the next parameter, which is ripple factor, represented by gamma. So in general, the output of half wave rectifier is not an actually purely DC value. So as we have seen in the circuit operation itself, we would have got the output as a pulsating DC. That is, instead of a straight line, we would have got it as in this manner, which means we will have a pulse in between, that is a discontinuous signal. So this pulsating DC, in the sense it contains ripples, so that is why we are getting the waveform in this manner. So these ripples contribute to a factor which is called as the ripple factor. So the measurement of ripples in the output with help of some factor is termed as a ripple factor. So in technical terms, this ripple factor is nothing but ratio of RMS value of AC component in the output to average or the DC component in the output. So this is the ratio of ripple factor. So RMS value of AC component, in the sense we will get it as IAC divided by average or DC component in the output, means we will get it as IDC. So we have calculated the value of RMS, which is nothing but the combination of both the AC component and the DC component. So we will get it as square root of IAC square plus IDC square. So we are supposed to calculate the value for what is IAC now. So from this equation, we can get the value of IAC as square root of IRMS square minus IDC square. So we can substitute this value of IAC in our ripple factor equation divided by the value of IDC. So this will be the ripple factor RF, that is gamma, which is equal to square root of IRMS square minus IDC square divided by IDC. So we have IDC both in numerator and denominator. So we can combine these two terms and make the value of ripple factor in an even more simplified way. So we will get it as IRMS by IDC the whole square minus 1 the whole square root. So this is for a general ripple factor calculation value, and this is the equation for general circuit. Now let us calculate this ripple factor in particular for a half wave rectifier. So for a half wave circuit, we have calculated the RMS value, which is IRMS is equal to IM by 2, and we have calculated the DC component in output as well, that is IDC, which is equal to IM by pi. So in the equation of ripple factor, we can substitute for IRMS and IDC prescribed for half wave circuit condition. So substituting that, we will get it as gamma, which is equal to square root of, instead of IRMS, IM by 2 the whole square, and instead of IDC it is IM by pi the whole square minus 1. So this IM square will get cancelled, and the remaining value will be square root of pi square by 4 minus 1, which is square root of 1.46. So after taking square root, we will get it as 1.211. That is, ripple content in the output is 1.22 times of DC component. So this is the actual particular value for a half wave rectifier. So this value of ripple factor can be minimized by using filter circuits along with the rectifiers. So this is the concept about ripple factor in general and in the half wave rectifier circuit. Next parameter, load current. So IL can be represented in terms of Fourier series equation as Im into 1 by pi plus 1 by 2 sin omega t minus 2 by 3 pi cos 2 omega t minus 2 by 15 pi cos 4 omega t. So after expanding this, we will get the equation in this way. So here after combining, we can segregate each term in terms of the respective values. So the first term 1 by pi is a constant value. We do not have any time oriented parameter or frequency oriented parameter over here, which is a constant value. So this value is called as average or DC value of load current. In the second term, starting with 1 by 2 sine omega t, here we have the time oriented parameter and the frequency as well, that is angular frequency. So this very first term, which is dependent on time, will contribute to what is called as the fundamental component of current. And after this particular term, everything will be with respect to the base term, that is, this will be the base for all the other terms in the further equation. So the second term minus 2 by 3 pi cos 2 omega t will represent what is called as the harmonics. Harmonics in the sense which is derived from the fundamental components. So all the remaining terms will be the harmonic components, whereas this first term will represent the fundamental term and the constant term will represent the average or DC value of load current. So ripple in the output, in the sense it is due to the fundamental and harmonic components, because here only we have both the frequency and time oriented parameters. So whenever we have ripples in the output, it is mainly due to these fundamental and harmonic components and not the DC value, because the actual output is supposed to be DC in a half wave rectifier. If we get any other waveform, that is pulsating waveform, along with this DC value, then it means that these are the sinusoidal components available. So because of these components only, we are getting the ripples in the output end of the rectifier. Next is peak inverse voltage, PIV. So the peak voltage across diode in the reverse condition is nothing but this peak inverse voltage. So it occurs at the peak of each negative half cycle of input when the diode is reverse biased. So when we have a waveform in this way, this half represents the negative half cycle of the input. So whenever there is a peak value in the negative half cycle of the input, we will get a corresponding peak voltage with respect to this input, which is called as this peak inverse voltage. So this happens only when the diode is in reverse biased condition. So peak inverse voltage of diode is nothing but the maximum value of secondary voltage, which is ESM. So which can be represented as pi into EDC under the IDC value is 0 condition. Next is transformer utilization factor. So as we have seen in the circuit diagram of the rectifier, we have seen we would have used a step down or stepped up transformer at the initial stage, because with that only we have required the AC voltage which is supplied into the diode. So the ratio of DC power delivered to load to AC power rating of transformer is referred as the transformer utilization factor. So with this parameter, we can identify, that is, we can calculate how much percentage of transformer is utilized for this particular half wave rectifier. So let us calculate the individual values of DC power delivered to load first, and second is AC power rating of transformer. Then let us divide it by the two things, so to get the ratio of this transformer utilization factor, and then we can calculate how much percentage of utilization is done here. So AC power rating is nothing but product of voltage ERMS into IRMS. So voltage RMS value is nothing but ESM by root 2, that is secondary voltage, and IRMS is nothing but IM by 2. So here the ERMS value is 1 by root 2 times and IRMS is 1 by 2 times. So this is about the sinusoidal waveform which creates a difference over here. So secondary voltage is nothing but purely sinusoidal waveform. So that is the reason we are getting it as 1 by root 2 times here. Whereas the current is always half sinusoidal over here. So that is the reason we are getting it as 1 by 2 times of RMS value. So multiplying these two things, we will get it as ESM into IM divided by 2 root 2, which is AC power rating. So we have calculated the denominator portion. Now let us calculate the numerator portion, and then we can divide the two things to get the transformer utilization factor. So the DC power delivered to load is nothing but product of ID square into the load resistance RL. We have calculated the value of IDC early itself. So IDC is nothing but IM by pi. Substituting that over here, we will get it as IM by pi the whole square into load resistance RL. So the transformer utilization factor is DC power delivered to load divided by AC power rating. DC power delivered is IM by pi square RL divided by AC power rating is ESM IM divided by 2 root 2. So solving this further, we will get it as TUF is equal to Im square by pi square RL 2 root 2 divided by Im square into RL. So before this calculation, we need to know what is the value of secondary voltage ESM, which is nothing but Im into RL. So here we have neglected the voltage drop across the forward resistance and source resistance. We have discussed about this neglection factor already. So using that, we can get the value for what is the secondary voltage ESM, and after substituting that over here, we will get the resultant value of transformer utilization factor as this way. So here Im square will get cancelled and RL will get cancelled. The remaining value will be 2 root 2 divided by pi square, which is 0.287. So this value of transformer utilization factor is very low, which means the transformer is not fully utilized in a half wave rectifier. So this is how we can calculate the value of TUF, and you can conclude if it is completely utilized or partially utilized for the corresponding circuit.
So we were seeing about the parameters of rectifier. So in that we will see about what is voltage regulation. So in general, voltage regulation means the secondary voltage should not change with respect to the load current. So that is the basic regulation work. So voltage regulation in the sense it is a factor about the change in DC output voltage as the load changes from no load to full load condition. So during the initial phase, we will not apply the load value directly, which means it is under no load condition. So when it is getting raised from no load to full load condition, during the variation of this particular load, what is the change with respect to the output voltage? So this ratio is defined as what is called as the voltage regulation, which is nothing but VDC under no load condition minus VDC under full load condition divided by VDC under full load condition. So NL represents no load and FL represents full load. So lesser the value of voltage regulation, better will be the performance of rectifier circuit. So this is the formula for what is called as voltage regulation. Now let us derive the value for voltage regulation in specific for a half wave rectifier. So for a half wave circuit, this VDC under no load condition will be equal to secondary voltage divided by pi, and under full load condition VDC will be equal to IDC into RL. We know the value for what is IDC, that is DC value of current, which is Im by pi into load resistance RL. Again we know the value for what is this particular Im, which is ESM divided by pi into the net resistance RF plus RS plus RL into RL. So RF refers to forward resistance, RS refers to source resistance, and RL refers to load resistance. So now we can calculate the value for what is percentage voltage regulation. So we have got the value for VDC under no load condition and full load condition as well. So applying that, the initial value of VDC under no load condition is ESM divided by pi minus under full load condition it is equal to ESM by pi into RL divided by RF plus RS plus RL divided by the value of VDC under full load condition. So again we will get it as ESM divided by pi into RL divided by RF plus RS plus RL into 100%, because we are calculating voltage regulation as a percentage here. So simplifying this, we have both ESM in the numerator and denominator. So we can take that outside and we can just simply divide it, and along with the value of pi we can divide. So the remaining value will be equal to 1 minus RL divided by RF plus RS plus RL divided by RL divided by RF plus RS plus RL into 100%. So simplifying this, we will get it as RF plus RS divided by RL into 100%. So this is the value for voltage regulation in percentage, which is nothing but the ratio of resistance, that is forward resistance plus source resistance, the numerator, and in denominator we will have load resistance. So this is the equation for a half wave rectifier. So here we can use this peculiar condition, that is neglecting the winding resistance, because we have seen in the previous parameter itself, in case if Rs is not provided, we can simply neglect, or if it is infinite also we can neglect it. So neglecting the winding resistance Rs in the above equation, we will get it as percentage voltage regulation, which is nothing but forward resistance divided by the load resistance into 100. Now we can draw a graph between load current and load voltage. So we will get the graph in this particular way, that is a drooping characteristics. So here this point refers to VDC under no load condition, and this point refers to VDC under full load condition. So it is ideal for zero regulation, which is practically not possible. So for practical condition, that is when it is increasing from no load to full load condition, the regulation also increases. So that you can see that from the graph also. So the graph of load voltage versus load current is nothing regulation characteristics, which is always drooping in nature, that is it is getting reduced over here. So this state refers to the drooping nature. So lastly, we can see what are the advantages and disadvantages of half-wave rectifier. And are the advantages of half-wave rectifier? So here we have used only one diode. So with only one diode, we can make this half-wave rectification. So it will be easy to design, and we need not require any center tap transformer, because you have used either step down or step up transformer. So these are the advantages. When moving into the disadvantages of half-wave rectifier, the ripple factor is very high, that is 1.21 value, and efficiency is also high, that is 40%, which means 60% of the output will be just ripples, which makes this particular circuit an insufficient one, that is inefficient one. And we have a lower transformer utilization factor and high cost. So to minimize the saturation, the transformer size will be increased, because of which we will have a high initial cost. So therefore, this half-wave rectifier, it is not used as a power rectifier circuit. So these are the advantages and disadvantages and various parameters of half-wave rectifier. So let us solve a problem in which we will be solving, that is calculating all the parameters we have discussed so far. So the question is, a half-wave rectifier circuit is supplied from 230 volt 50 hertz supply with step down ratio of 3:1 to a resistive load of 10 kilo ohms. The diode forward resistance, that is RF, is equal to 75 ohms, RS is equal to 10 ohms. Calculate maximum average RMS values of current, DC output voltage, efficiency, voltage regulation, and ripple factor. So we have derived the equations for all these parameters, and we have the necessary input values also. Using that, we can proceed how to solve this particular question to calculate all these parameters. So the first data given are RF is equal to 75 ohms, RL is equal to 10K, RS is equal to 10 ohms. So to calculate the values, first we need what is EP, that is primary voltage, that is RMS value, which is given as 230 volt. Next, the turns N1 by N2 is given as 3:1 ratio. We need the value for what is N2 divided by N1. So we will get it as 1 by 3. N2 by N1 is nothing but the value of secondary voltage divided by primary voltage. So this is nothing but 1 by 3. We have got it. So we can calculate the value for what is ERMS from this value divided by EP is given as 230. So 230, which is equal to 1 by 3. So solving this, we will get it as ES RMS value, which is nothing but the secondary voltage of RMS value, as 76.66. That is 230 divided by 3 volt. So this value of ES RMS refers to RMS value of transformer secondary voltage. So this is the value of ES RMS. Next, let us calculate the value for what is ESM actually, which is nothing but root 2 into ES RMS, because for everything we will need the value for what is ESM. So we can calculate the value of ESM first, which is root 2 into ES RMS value is nothing but 76.66, which we have calculated now, into 76.66 volt, which is nothing but 108.42 volt. So we have calculated the value for what is secondary voltage. Now let us calculate the value for IM first, which is the maximum current value, which is equal to ESM divided by RS plus RF plus RL, which is equal to ESM is 108.42 divided by RS is 10 plus RF is 75 plus RL is 10 into 10 power 3, since it is kilo ohms. Solving this, we will get it as 10.75 milliampere, since it is current. Now let us calculate the average value of current, that is IDC, which is equal to IM divided by pi. So IM is 10.75 milliamperes divided by pi, which is nothing but 3.42 milliamperes. Next is IRMS value, which is equal to IM divided by 2. Again, IM value is 10.75 divided by 2, which is 5.37 milliamperes. So these are the values that we have calculated now. So the formulas for IM, I average, IRMS, everything we have derived earlier. Using that only we have solved all these things. Next is DC output voltage, that is EDC, which is equal to IDC into RL, which is IDC value we have calculated earlier, which is 3.42 milliamperes. So into 10 power minus 3 into RL value is 10 kilo ohms. So 10 into 10 power 3, which is equal to 34.22 volt. Now let us calculate it for DC output power, which is PDC. So value of power is product of voltage into current. So it is EDC into IDC. The value of EDC is 34.22 volt into IDC value is 3.42 milliamperes. So into 10 power minus 3, which is equal to 0.117 watts. Next, let us calculate the value for what is AC input power. So AC input power, in the sense it is PAC, which is equal to I RMS square into RS plus RF plus RL. So the value of I RMS is 5.37. We have calculated it 5.37 into 10 power minus 3, because it is milliampere square, into RS value is 10, RF 75, RL is 10 into 10 power 3. Solving this, we will get it as 0.2913. Since it is power, we can measure it in watts. Next, we can calculate what is efficiency, percentage efficiency, which is nothing but PDC divided by PAC. So this is the reason why we have calculated the value for PAC here into 100%. So PDC value is 0.117 divided by PAC is 0.2913 into 100%, which is equal to 40.19%. So this refers to what is called as efficiency for the given half wave rectifier. Next is about voltage regulation, for which we have to calculate the voltage under no load condition and full load condition. So first let us calculate under no load condition, which is nothing but ESM divided by pi. So the value of ESM divided by pi, after substituting that, we will get it as 34.512 volt. Next, under load condition, VDC under full load, which is nothing but the value of EDC, which we have calculated earlier, So this is 34.22 volt. So with this we can calculate the value for what is percentage voltage regulation, which is VDC under no load condition minus VDC under full load condition divided by VDC under full load condition, which is equal to the value of VDC under no load is 34.512 minus 34.22 divided by 34.22 into 100 percentage. Solving this, we will get it as 0.8533 percentage. Finally, we can calculate what is the value of ripple factor. So, ripple factor RF is nothing but square root of I RMS divided by IDC the whole square minus 1. Substituting these values, we will get it as 5.375 divided by 3.422 the whole square minus 1, which is 1.211. So this is the value of ripple factor. So these are the values for half wave rectifier which is provided in the question. So this is how we have to calculate each and every parameter. So in a single problem we have covered almost all the parameters that we have derived so far. So in case if you have any doubt solving this question, you can post it out in the comment section. Thank you so much, friends.